I'm Asmita, and yeah, today we are going to look at the fully homomorphic encrypted applications. Uh, we're first going to look at some challenges, and then performance-wise, as well as some vulnerabilities that might be there, which is not necessarily in the homomorphic encryption theoretical side, but more in how it has been implemented in current systems or how it is handled. And yeah, so it so this is what I'm the outline for today's talk. And so first we are going to look at the risk of outsourced computations, and then we are going to get a little bit of background on fully homomorphic encryptions, and followed by challenges in designing systems which are based on this encryption. And then we are going to move on to some privacy pitfalls and some experimental setup and results. So first, let's look at, wait, let me move this tab somewhere, maybe here. Yeah. Okay. So first, we're going to look at the risk of outsourced computation. Let's imagine a scenario when we do a search like, okay, Google, find some coffee shops near me. So when you do that, Google knows that, you're looking for a coffee shop, your location, when you perform this search, and the probability of how often you do this query. Now, with the recent advances in cloud computing, obviously we leverage the advances, and then we see that there has been a shift in the amount of data storage on third-party servers. So the client does some query, and then a lot of the computation is done on the server. So am I audible? It just shows a pause or something.
Yeah, I can hear you.
Okay, yeah, no, there was like a pause. Okay, cool. And though the cloud storage is convenient and cost effective, a lot of sensitive data such as medical or financial records can be compromised in such environments. So along with what Google knows in this particular scenario, there's more. The server knows what answer was given to you, how you do the search. So the question is, how do you do the search without sharing this information with third parties? And then the final question is, do we really care about the data exposed for our caffeine fix? Of course we don't. But let's say in a scenario where you are searching something that's a medical record, or something related to your investment, some financial data. So in that case, you don't want it to be leaked. And there are multiple fixes to this. There's secure communication, multi-party communication, but today we are going to focus on fully homomorphic encryption, where once you send in the data, it stays encrypted through the entire process. And irrespective of whether the channel through which you're sending data, or what you're doing on the server, or when the data comes back, they may or may not be secure, but the data itself is encrypted, and it's in a different format then. So in this scenario, this example that you see here, so the client has needs to compute a certain function on their data, which is X. And then in order to do this, they encrypt the data and they send it to the server. And then the server performs that computation, and then comes back and then gives it back, which can only be decrypted by the client who has the secret key. And this process ensures that the data X is never compromised, even when it is being sent to the server. So now that we get a general idea of what a very generic fully homomorphic encryption scheme is, we're just going to take a brief look at what are the different homomorphic encryption schemes that have been proposed so far. So some of them are in terms of Boolean circuits, some of them are exact arithmetic, and some of them are approximate arithmetic. So the ones on the left column that you see here, these are bitwise approaches, and then the rest of them, the exact arithmetic as well as the approximate arithmetic, are more wordwise approaches. And for the rest of the talk, the challenges that we're going to see, and then the different processes, like, the different kernels and homomorphic encryption, we're primarily going to focus on word-wise approaches. So given this particular template that we saw, so the client side, there's a client side and then there's a server side. Now the client side is responsible for encryption and decryption, and then the server side is responsible for homomorphic addition, multiplication, and other ciphertext maintenance applications, operations. So first, we're going to look at what happens, the different operations. We're going to do a brief overview of that, and then we're going to look at challenges in each of these. So in the first one that we have here, we have the encryption, or, in the other case, you have the decryption. So we're going to look at encryption first. So you have plain text vectors which are encrypted as ciphertext, which occurs as a pair of polynomials. So encrypting, so a message where you have a message vector, and then you have like a certain noise being added, as well as the secret key being used, and then you encrypt it to a larger space, which is the ciphertext space. And in this particular pair of polynomial that you see here, is the ciphertext is usually very large because it's in the polynomial domain, and each ciphertext coefficient can be very wide, which is like, it's reported by some of the papers, up to 1,000 bits, 2,000 bits. And so this is one of the problems, like, of the ciphertext being very large. So every time any computation has to be done, instead of like this small message that you see here, it has to be done on a ciphertext, which is a pair of polynomials, and each element is like very wide. So one solution is, the problem being like, computation with wide coefficients costs a lot. So one solution is using the residue number system. So this is like an algorithmic optimization that has been done to handle fully homomorphic encryption. And it can represent, what it does is you have this very wide polynomial modulo q, and then instead you express it in terms of like L polynomials, each with like a smaller module qi, such that the product of them is equal to q. And if you can see the transformation here, like, you had this polynomial, and instead you're transforming it into smaller polynomials which have smaller bit width. And in doing that, you are it's easier for this to store and then handle like operations in hardware, as well as algorithmically. So now that we know what, so most of this encryption is done on the client side. And then this encrypted data is sent to the server side. Now, our main challenge is like is a lot more challenges are on the encrypted data. So after it has been encrypted, because it's very large. So you see, like, already the data has expanded. That small message that we had, that has expanded so much. And then all the other operations, like, if you perform addition, multiplication, or other things to maintain this data. So a lot of challenges then come on the server side. So now we are going to look at some of the operations that happen on the server side. So addition, like, of course, there are certain overheads to homomorphic addition, but every time you do a homomorphic addition, there is the noise is additive. But but every time you do like a multiplication, of course, the noise grows. So if we look at a scenario, let's look at a scenario where of homomorphic multiplications. So both, like, homomorphic addition, like all the three operations that are there, it's complex. But in this particular scenario, you can see that you're doing a multiplication. Now, in homomorphic encryption in that domain, if you just do a multiplication, of course, the noise grows. And then there are certain challenges. In order to, and once you do the multiplication, there has to be an additional step known as key switching. Now, this key switching is done because multiplication and rotation operations produce polynomials, which are only decryptable uh, with keys which are different from the original secret key in the course of the computation. And then in order to make these polynomials decryptable with the actual secret key, this key switching has to be done, which multiplies this polynomial with a public key, which is also called the evaluation key. And now this key is obviously one requirement is it has to be very large. So you can understand how complex this operation gets. Just not the multiplication, but with the multiplication and the key switching. Both of them have a very high computational overhead, as well as, you have this memory overhead, like where you need this key switching hints, or, in other words, what I mentioned, the evaluation key. So it's very expensive. And then algorithmically also, it's operationally, it has like n square complexity. So one thing that has been done is using entity, which is the number theoretic transform, which is similar to DFT because of the complexity. So instead of having like this convolution, here you're changing it to it can be performed in using entity instead of doing it in n square. You can do it in n log n. And as you can see here, this transformation, instead of doing this convolution operation here, you're doing like in the entity domain, you're doing like an element-wise multiplication. So, but even then, you have to do it like every time. So imagine like, every time you're doing this multiplication, and there are multiple multiplications that you have to handle and you have to do when you are carrying out a homomorphic encryption. And even then, like, if you sum it all up, there is a very high compute overhead. So now we move on to the next homomorphic operation that's very common in most applications that are encrypted using FHE, which is the rotate. And what happens is, you have a ciphertext and you rotate it by key positions, and usually it's implemented using automorphism. Now, what happens is, you have your index I, and then in order to do this rotation, the new index is denoted by this formula. So for example, if you have k is equal to 2 and n is equal to 1024, you get your new index for, let's say, if your initial index was A205, it goes to A5. And in order to do this automorphism as well, you again need like one key for each automorphism, and then you need to do a key switching. So both multiplication and rotation needs this key switching in order to have like the original ciphertext, which is actually decryptable by using the original secret key. And this also incurs like another significant overhead, because first, we're going to see it later on as well in the slides as it progresses. And there is like a additional storage overhead because you need this key for every rotation. And also you need keys for the multiplication operation as well. So now we see that, we saw some primitive operations, but we also came across this thing called key switching. So which is a part of, what we call as ciphertext maintenance operations. So now we're going to look at some of the challenges of handling the ciphertext maintenance operations as well. Like what they are and what they do, and what are the challenges, how they are handled in FHE, because they also contribute significantly. Apart from the primitive operations themselves, they are a huge contribution to the whole FHE calculations. Any questions so far? No? Okay.
Wait, I saw the question in the chat. The
Okay.
question is how a residual number system reduces the cost if still all large queues, small polynomials need to be processed.
Oh, yeah, sure. That's a really good question. So what happens is, instead of, working with 2000 bits wide data, you still have like a very large data to operate, but instead of each element being that wide, you use like smaller, because you're doing like, you're reducing like the large queue into smaller queues, so your bit width is reduced. So you still have to handle a large ciphertext, but you don't have to handle each each element in the ciphertext is smaller. Does that make sense? You're reducing it from 2000 bits to, let's say,
Yeah, okay. Okay, so if it is like reducing, you are reducing, let's say, from 2000 bits to, I'm just making up some number, let's say from 2000 to 100.
yeah,
So
yeah.
then you have, but I'm assuming you still have 20 smaller polynomials, right?
Yes, of
So,
course,
but
of course.
then you need to process all of them 20 smaller polynomials. If yes, how it reduces the cost? Or is it like they are processed in parallel? I don't
So
know. Just trying to understand.
sure, that's a great question. Yeah, so you can actually leverage some amount of parallelism if you have smaller polynomials, right? And we're going to see later, like, two variants of parallelism that has been explored in, existing literature, and you can process it in parallel. Obviously, again, it's based on your resources, but this is more like an algorithmic optimization that has been done. So it's assuming that, you will have resources, you will have more resources to actually operate on smaller bit widths, because our systems are designed to handle like smaller bit widths. Our systems are not designed to handle uh polynomials which are like 2000 bits, right? So that's how it is. It's still a significant, you're absolutely right, it's still a significantly large data, and it's a significantly very large cost to operate on it, to use that data to operate on the ciphertext, do anything on the ciphertext.
Okay, thank you.
Okay, so now we come to the operation of key switching. Now, key switching is performed both for multiply and rotation, as we had seen earlier in the pipelines, and then you have your public key, and then you get like this intermediate ciphertext, and then you do key switching to get like the actual ciphertext, which is decryptable. And the size of the public key is often larger than the ciphertext, and then this rotation require now for rotations they require a separate key for each rotation. And imagine you have to store all these keys, like these keys have to be readily available, you every time you do a rotation, and these keys, and it's not like numbers, it's not integer or floating point numbers, it's polynomials. So these are very, very large, and storing this, of course, incurs like if you intend to store it, it incurs a very high memory overhead. So there is like along with the problem of compute overhead that we have seen earlier, in the operations themselves, the ciphertext maintenance operations have this memory very high memory requirement. So another operation that is done to maintain the ciphertext is modulus switching. Now, uh, it is more detailed, but I'm just going to do like a brief overview. So it can go like modulus up or modulus down, which means that, you just play around with the modulus Q. Sometimes, in order to control the proportion of noise, in, initial FHE implementations, this Q is reduced, and then, it can only be reduced to a certain point, like, you still need to have this one particular factor here. So L, like, which you see here, we had seen this matrix earlier, like, when you are actually doing the RNS. So this is like, the L here is like the multiplicative depth, which determines how many, the longest chain of homomorphic multiplications that you can do in the computation. So often, like, there are like certain implementations or libraries that you're going to see, which are going to call this rescaling. Now, this modulus switching or the modulus down operation is very good for shallow computations. But what happens, when you lose this entire multiplicative depth and you're still not done with your set of multiplications that you need to do. So what do you do for, like, deeper computations? So what do you do? So we're going to move on to very, very important. I think you've heard this term a lot of times, and it's a very important component of FHE operations, which is called bootstrapping. So what bootstrapping does is, you have this set of multiplications, and then you're reducing, like, in the last slide, you saw that you're reducing this modulus, you're removing the last row. And instead of, like, when you're left with just, like, one row in that particular in the modulus, so what you do is you refresh the ciphertext, you refresh this particular ciphertext to enable unlimited computations and then recover your multiplicative depth. Now, bootstrapping obviously consists of, the some operations that you see here. One is the modulus switching, and what it does this time is it extends the modulus. So when in the previous slide that we were seeing, like I said, you have modulo up and modulo down. So here it's more like modulo up operation. You're doing a rescaling where you're increasing the modulus in order to gain this depth. And then you have some linear operations, which is basically a homomorphic evaluation of DFT on encrypted data. And then you have some nonlinear operations, where you have a polynomial approximation followed by some exponentiation. So, and a lot of the time in bootstrapping is spent on multiplication and rotation. And then, as I mentioned before, you need a certain evaluation key for every multiplication and rotation. And what happens is the reuse, as the reuse of this particular key is very low, and each of these keys are very large. So there is like a problem of fitting these keys on the chip. So even the bootstrapping procedure has a very high memory overhead. So most operations that we have seen so far in the homomorphic encryption pipeline, they incur very high compute overhead or very high memory overhead. So now we are going to move on to some of the challenges. We're going to summarize, like, the challenges in designing FHE systems. So all primitive homomorphic operations rely on big polynomial arithmetic, which again is more complex. And so our first question is how to accelerate this particular domain. Like, we saw like algorithmic optimization such as RNS and NTT. So then the question comes how to accelerate NTT. And then there are, the ciphertext maintenance operations that we saw, which have many computations, and then, you're limited by either on-chip memory resources, or, if the keys that we saw are off-chip, then how, like, how do you handle that? How this is again limited by off-chip memory bandwidth, and you only have limited memory bandwidth. So these ciphertext maintenance operations also consume up to like 80% of the execution time. And then the question comes, how do you accelerate these operations? So accelerating entity, like, the first thing is you have very high computation complexity. So in order to deal with that, the question was there before. So you can execute multiple polynomials concurrently. Now, this depends, again, it depends on how much resources you have on the hardware side, or whether or not uh, mm, assuming you have like a lot of hardware resources. Again, remember, this is happening on the server side, so it is assumed that you will have enough resources. And then we have intensive memory accesses. So in order to handle that, a lot of works have used HBM or SRAM, and or generate some parameters on the fly, which can be done. And then in order to another problem of handling entity, any operation in that domain, is the lack of generality. What it basically means is that you can't generalize, you can't choose that, okay, I'm going to use this DFT acceleration over that. So it's again because of it depends on the type of application, it depends on which homomorphic scheme is being used. So it's very hard to generalize the entity acceleration itself, though some works have attempted to do that. And we're going to look at a brief overview of some of the works that have been done so far. So one way to do this is use hardware software co-design. So you tune your programs, you tune your FHE application to exploit some particular acceleration for entity or for one application, and then you tune your other application. Let's say you have one application which does like a credit card identification of fraudulent transactions, and then you have this ML application which does that, and you have to, it is probably more, it benefits more from higher compute acceleration, so you're going to tune it to that, and then you can configure some part of it to operate on a specific hardware, and then another FHE application can be configured to be operated in a different way. So one ciphertext maintenance operation was key switching. So key switching consists of both multiplication and addition operations, and this entity problems that we saw earlier in the previous slide. And there are two things which have been highlighted by works that have been done so far. One of them is, as you can see here, because they call it the residue polynomial level parallelization. And this is again achieved by distributing multiple residue polynomials to different processors, and then this is better for multiplication or addition for the frost basis conversions. And the second parallelism that a lot of works leverage is the coefficient level, where multiple processors collaboratively execute operations for a single residue polynomial, which is again which is good for entity. So the question is, which one is better? Like I mentioned before, it's really hard to answer that. And the reason being, you cannot generalize it. You need further application characterization to determine which one to choose. So there are works which have shown that let's say there is an ML privacy model, and then privacy preserving machine learning model which does some operations, and then for them multiple distributing it across different processors is better. So this characterization is again very important. So it is quite hard to answer whether or not you will benefit from a specific accelerator, or whether why not use GPUs for it. So the second is we talked about bootstrapping, we talked about certain challenges. Of course, it was there was a lot of compute overhead because of the multiplications and rotations which are there inside bootstrapping, and as well as it since it does this multiplicative increase in the multiplicative depth in order to regain it, so it does consume a very high percentage, which leads to an increase in the size of the, the Q modulus, and well as the degree of the ciphertext itself. It has to be very large. And along with that, there is memory overhead of storing the keys themselves. So prior work has proposed, specialized unit to tweak the different parameters that you use while doing the bootstrapping process, and also employed, the coefficient level parallelism, where multiple units actually contribute to evaluating a single polynomial, which has been shown to be faster. And one of the works is it was proposed we're going to see in the future slides. It's called BTS. So it did show significant performance gain over existing accelerators by accelerating the bootstrapping kernel in FHE applications. So next we move on to just a brief overview of prior FHE techniques. This is not an exhaustive list. It's just some of the major techniques that have been more popular among the architecture community. The most recent work, as you can see here, which was actually showcased this micro, it's supposed to be agnostic to the hardware, and then the type of a lot of them support. So some of them are more tiled towards bitwise approaches, and then most of them, since the word wise approaches are more popular, a lot of them are towards accelerating the woodwise approaches. The latest techniques that have been proposed do handle the problem of bootstrappable algorithms, because in homomorphic encryption, there are applications real-time applications which do not really need the bootstrapping. So they stop at the modulo down operation. They do this modulus, and then there's enough. It's enough to handle the noise that you incur because of multiplications, the growing noise. So, but there are more applications, realistic applications, which need bootstrapping. So there are works which does address the acceleration of that, either very low level, primitive operation level, which is the multiplication or rotation, or at a more high level, having some specialized unit, or just focusing on the kernel. So both memory and compute continue to be a bottleneck for FHE encrypted applications, and application-driven design approaches can sometimes benefit from specific tuning, like ML inference. And the question is, can you have support for these are again very open-ended questions. Can you support both word-wise and bitwise FHE schemes at the same time? Can you do something fundamentally different that supports both of them? And like I mentioned, I think it will definitely benefit if an enhanced hardware-software co-design is used, and use of better compilers to actually process FHE-tuned code. And another thing that could be a possible direction is connecting multiple FHE accelerators and enabling network co-design. So this is pretty much my understanding of how what are the performance challenges in fully homomorphic encrypted applications. Now we are going to move on to some of the although FHE is airtight, and we're going to see some of the privacy pitfalls that might be there in existing implementations and just FHE systems. Any questions so far? No? Let me see.
I think chat has a question.
Yeah.
Is there any publications related to this talk? So But
Oh
I
yeah,
think,
of
Mhm.
course, yeah. I can share it. I can share it. So a lot. So we are going to look at some of the the privacy side of it, which is what I have um had have a publication on. So yeah, I can share it in the chat after this.
Sure, thanks.
Cool. So the privacy problem, theoretically, like I said, FHE is airtight. And the question is, are there any possible side channels? Of course, the answer is there's always side channels. That's what security researchers try to say about everything. Um, there has been one published work, which is not, which is work from NC State, which has this, this is like a code snippet from their paper, and it targets the seals. Seal is like one of the FHE libraries that I used, and it targets the Gaussian sampling operations. So what it does, it has these it looks at branch operations, and then these non-uniform value assignment, and then some negation operation, and then that's how it. Oh wait, I don't know why this. Okay, anyway, I'll just talk about it. Yeah, so it targets the Gaussian sampling operation. It necessarily does not say that this is what what the key was, or but it does show that the plain text encryption security, which is usually like 2 to the power 128, it comes down to 2 to the power magnitude of 4. So that is like a significant security loss, and they are able to show it. So my question is, what are there any other problems with the FHE implementation? So we did like a small initial analysis on characterizing FHE memory side channels in FHE applications, and a part of this work has been done in collaboration with IBM Research. So we move on to our use case, which is a database query application, which has been, of course, encrypted with FHE, where someone on the server side knows the memory layout of the database, and what they do is analyze memory traces from the operations that you have on encrypted data. So your data is still stays encrypted, and we try to understand how what operations have been done. So the question is, can we recover the secret key from FHA encrypted traces? The answer is no. But what else can the attacker do? Now, traditionally, from a security perspective, even if you can leak one bit of information, or if even you can knowing even one bit of information is dangerous. So what we are going to do is we are going to see if we can detect any obvious patterns, like memory access patterns, which are unique to each query. So the notion of we come to this notion of trace distinguishability. So the trace distinguishability is whether an adversary can distinguish between unique queries from the database. Let's say you're querying for a country, which, let's say, find the capital of Spain, and then versus find the capital of Mexico, and then or queries which are found in the database versus queries which are not found in the database. So in order to do that, what we do is we collect some traces, and when we try to say that this particular this trace belongs to this query, and this itself, technically homomorphic operations are supposed to be indistinguishable, right? So if you do that, it is still a leakage of information. So what we do is we say that distinguishing patterns act as side channel information to the actual query. And we use machine learning based classifiers as the adversary. And then these adversaries are trained on probing with synthetic queries, and then distinguishes the actual user query, as in the label of the query. Not the user. The user is still it's assumed like, a user is doing like multiple different queries. So we look at, some of the experimental setup. So we use the HELib framework with the BGB scheme. And this is the trace structure, which is like a very generic trace structure that is used in a lot of memory access pattern based performance optimization. So we specifically look at destination and source memory addresses, and the traces were collected using pin tool. So we only have virtual addresses. And what we do is we first assess the spatial spread by clustering addresses at like a block level granularity. And then we have like these 3 key regions based on the area of the code that we profile. And then we generate like, temporal distribution for each region, and we try to identify, and we then try to feed this temporal distribution into the classifiers and then identify whether or not they are distinguishable. So in order to better understand like, what or why, like, we do some analysis on different kernels that are there in the database search or the HELib search code that was written. As you can see here, we obtain this flame graph data by attaching perf to the search algorithm, and then we look at different flame graphs from different queries, and then a lot of time is spent in the power, rotate, and product operations, as you can see here. So you have this main operation, and then even like, even in the prior slides that I mentioned. So a lot of time is spent in these operations. So what we did next was we took a few comparative flame graphs. So we look at, 2 different flame graphs for 2 different queries. So, and if you look at these, they are almost identical, right? So you have this total product where you spend 41.15%, and here you spend 41.84%. So it's really hard to distinguish between what it says is, to just like look at 2 different queries and say, this is different from the other because the time spent in each operation is very similar. So hence we switch over to this different mode of vulnerability, which is memory access patterns. And this is not something like, that I'm coming up with. This is not brand new. So this has been like explored in terms of like, prior encryptions, which is the AES, where you have like a certain trace here and in the SBox function, and then these attacker goes into the trace and identifies reads which are like very specific, which look different, or just like does a clustering. If you look at a trace and you're an attacker, you do this clustering, and then what you do is you try to allocate the brace address, and then you look at the offsets, and then once you given the plain text, and you XOR it with the offsets that you get from your studying the trace, then you can recover the secret key. So memory access patterns in general have been used. What I'm trying to say here has been used as a side channel, and like this is something not, but we are looking at it obviously from a different perspective, which is trace distinguishability. So here I'm going to show you some results that we have based on our trace distinguishability notion. And you have an adversary who's classifying whether the query is existent in the database or not. We do it with 5 existent and non-existent queries. We have 20 traces for each query. And the peak accuracy that you see here is like 80%, which is like really high. Like if an user is doing a query, and then let's say, which might seem like a contrived case, but let's say the database is like of size 3 or 4. So what is stopping the adversary from saying like, which query it was in the database? And once you know what the user was querying, it is incredibly like insecure, right? Because you can tell what this user will query multiple times. So that again is like an information leakage. Now, another thing that we did look at is the multi-class trace distinguishability, where we have a much lower peak accuracy, which is 45%. But if you look at the top K scores, which is, how often the predicted class falls in the top K highest probabilities, it's 80%. So like for 6 labels, like in the top 6 scores, it's as high as 80%. So if you are, and this 45% is like, here we have like 12 unique queries. So it's still much higher than randomly guessing, which is like 1/12, right? So it's still much higher than randomly guessing a class, right? From an adversary's perspective. And if we did this experiment, of course, with like, which I don't show here, with like fewer labels, let's say 6 labels, 7 labels, and the accuracy is higher the lower the number of labels, which makes sense, right? Like if you have fewer labels, it's easier to guess. Now we move on to like the end of this presentation, where the question is like, side channels. Are side channels really a threat to privacy for FHE applications? And it's not necessarily the FHE in theory, and it's more like the implementation, or how the noise is added, or how the noise is modeled. And memory access patterns are just like, one such side channel, and we show this is trace. We show the notion of trace distinguishability based on the memory access patterns. And we are currently extending the use case to a privacy preserving machine learning workload for detecting credit card transactions, which is again a more realistic scenario than querying like the country capital. And if we do show distinguishability there, it means that, an adversary can say that whether or not this transaction is correct or fraudulent. And once they know that, can they do something else with it? That's the question. So again, like, some countermeasures need to be developed along with, the amount of accelerator research that we have. We do need some countermeasures for spotting like side channel leakage from FHE implementations, or just like FHE operations on servers. And that's the end of my talk, and I'll take any more questions you have now. Maybe there are some on the chat, or
I have a question. So the function that you show that contains the noise, that there's a if, else, if, and else based on the noise. Where does that function appear? Like, in what code is it doing that?
The one that is from the previous work, is that let me just pull up that slide.
Yeah.
Is this the one?
Yeah.
Yeah. So this is from the encryptor that you see here in the encryption itself. So this is this is part of like a prior work. And what it targets is, it tries to recover like some coefficients that are there, and then explore and then estimate like the other search space.
But this computation is something that is done in a client, right? So when you produce the ciphertext, is that right? Okay. So whereas the work that you did on the database traces, that one is the code that runs in a server, which is.
That's right. Yeah. This is let me just pull this up. Yeah, so this is entirely like on the server. Like you can only collect traces on operations on the server side, right?
Right. So what's the explanation? Where does the side channel come from? Because I think at the server side, all the operations kind of use ciphertext. There's no encryption.
There is no, yeah. All of them use the ciphertext. So it is completely, so like I said, it's not, I am still not at a point to make a claim that you are going to convert, like, because you're just looking at traces, but you can say you can say on the server side, and like, is this ciphertext different from that? Because that's not what it's supposed to happen, right? Like,
Yeah.
if you can say that this ciphertext is different, then then even that is like a form of, even one, like I said, even one bit of information leakage is information leakage. So this, like I said, I'm still looking at, if you remember the flame graph here, I'm still looking at, the different kernels, and if I can pinpoint,
Right.
from where exactly here, from which particular kernel here, this problem is coming. Like, is it the key switching part? Is it like, special primes? Is it the whole relinearization? So which particular kernel is actually giving, like, memory access patterns, which are like distinguishable, because they are creating a certain footprint on memory. And it's the same application, right? It's the same operation that you're doing, the same number of multiplications, the same number of rotations. So what is exactly, and that is again like something I am like, it's ongoing research.
Okay.
So yeah, so that's why, I mean, database query was an easy application to start with, and I mentioned later on that I'm moving on to this fraudulent versus non-fraudulent. So in that case, it's a more realistic scenario and easier to pinpoint where we are at.
So okay, so in that case, maybe I ask a question about the database itself. So the database, I don't know how a database that records information in ciphertext, what do they look like? So is it the same, like, you have a bunch of tables, but the key is in ciphertext, the record in ciphertext? Is it something like that?
Yeah, so they do like encrypted the way this one is implemented. So both the database is encrypted. And it's like, that's why it's like an airtight system. So both the database is encrypted and the query that you're doing is also encrypted. So it is still like, everything is still like, it's ciphertext into ciphertext. So you are still doing, and then you're masking it, and then there is a mask operation that is there in, like, in this BGV search that is implemented. And then that mask determines whether or not it's a match.
Yeah. I mean, I'm thinking of the traditional database. You will have some index tree that allows you to
So
locate the record pretty fast, right? Because it's sorted.
Yeah. It is sorted. And I think like even here the database is also sorted.
With ciphertext, I'm not sure, like
but you have to go through every query in the database, I think. So
so you
like,
have to check against every record, right? So
every record in the, sorry, not query, every record. You have to do this, like, you have your query, and then let's say you have 100 records in the database. You have to do that operation with all the 100 records. So so, and then you get only one match. Like, it has to be like, the mask, the masking operation which they do has to match with only one. And then you find out whether, and if it doesn't match, then it's like a no match. So
so could it be that the side channel is from, like, once you find a match and then you terminate the computation early, terminate the sets, so then it's a problem, right? Because
yeah. I mean, so the thing with homomorphic systems is they don't have like a if else thing, right? So if you do find, so the match, I think the masking or the match happening is like after all the records have been like, you go through all the records and you sum up the result of those computations, and then you try to come up whether or not it's a match. So unless there is a control flow, if there is a control flow, of course, control flow will be a side channel, right?
Yeah, that's right.
Yeah, control flow is generally avoided in most like in the applications that exists right now, which are used. But yes, if you do have like a control flow, it has to be.
Yeah, that's right. Yeah, so it's inefficient for many reasons, not just for processing in ciphertext, but it's also not being able to sort or use an index tree or things like that.
Yeah. It has to be
Makes
like
sense.
anything to. Are there sorting algorithms which are FHE encrypted? I'm not aware of that though.
Yeah, well, I doubt it because the comparison is really expensive, much more expensive
Comparison is
than
very expensive. Yeah.
multiplication. So sorting requires comparing. Yeah. It's
Yeah.
very strange computation model actually, but it's interesting. Yeah.
They do this I heard this, I think even this time, even like in one of the conferences lately, they told like there is even the ReLU operation, and even that is approximated, right? Like ReLU activations in machine learning, like if it is FHE, then even that is because like you mentioned, comparisons are very expensive. So I think with sorting also they will have like some kind of approximation for the comparison.
Okay, thank you.